Okay, we'd like to begin our presentation by expressing our appreciation for you taking the time to listen to our presentation. And the purpose of this project is to maximize distillation column efficiency, thereby maximizing profit. And in this particular case, the composition of the light key in the distillate is to be 95%, and the composition of the light key in the bottoms is to be 5%. And one of your concerns may be the quality of our model, but throughout this demonstration, this presentation will demonstrate the quality and applicability of the model. So the model was developed to simulate how a distillation column will respond to changes in disturbance, variables, and set point changes. Some assumptions were made to simplify the model. Some notable ones include constant relative volatility, constant tremolar holdup, and liquid feed at bubble point. The basis of the model is a simple overall non-steady state material balance and a species balance on the light key. And as a reminder, our goal is to fix product stream compositions, and the disturbance variable which makes this difficult is the feed composition variance. And we manipulate the reflux ratio and fraction of the feed going to the bottoms in order to fix the composition in the distillate and in the bottoms that we desire. And the closer we can keep these compositions to their set points, the more efficient we run and the more money we make.
Okay, to simulate our distillation column, we first created a block diagram in Simulink. We first performed a double test in LoopPro to get our tuning parameters, and after we got that, we put that into our transfer functions, and from the IMC correlations we got our tuning parameters for our PID controllers, and we also added the date time in both our non-interacting and interacting processes. And also after we added the feed-forward controller in our interacting process, we did a set point tracking and disturbance rejection test in both our processes. Oops. Is it this one? Okay. We did a set point tracking, and we did a 5% step in our distillate composition. And as you can see on the diagram on the left-hand side, in our interacting process, for the bottoms composition, there wasn't any much deviation.
Awesome, thanks, John. On the right-hand side, you can see the results of our disturbance rejection test we did. We did a 5% step in the feed change. That's shown on the red line there, and its axis is on the right-hand side. So just note that they're scaled differently there. On the left-hand side is the bottoms composition, and so you can see the three different controllers and how they responded. The non-interacting is the blue one, the interacting is the green line, and the model predictive control is that orange line down there. And so it looks like there's virtually no change. On this next slide, we have just the model predictive control, so you can see on the left-hand side the reflux ratio and the fractions that went to the bottoms, how they responded. This was a doublet test this time. And then on the right-hand side you can see the change in bottom and top composition. And there's about a 0.03% change. So it did really well at modeling that. And that's what we saw overall, that the model predictive control was the way to go to model this distillation column. Any questions?